So this is our experimental setup. No PPE is required. I'll take you over here. Here's our LiDAR sensor. 30 centimeters away is our test specimen mounted on this stepper motor. That's controlled by Arduino, and we'll be using the DAC, the NI DAC, to record our data. And we'll show you a quick example of how it works. So we'll start the VI and then we'll power on the motor. And you can see as the cube turns, it records the distance the way that it is.
We are attempting to build a low-cost 3D scanner with an acceptable resolution and accuracy that can act as a quick reference for volume measurements of small objects and provide a 3D model of the scanned object. Using a LiDAR sensor, stepper motor, and 3D modeling software, our scanner is expected to take distance measurements and create an accurate 3D replica of the object being scanned. Comparing the resulting volume of the 3D model to a known standard, either using a commercial 3D scanner or water displacement, the results from our scanner should be within 5% of the actual volume of the object.
For the course topics we will cover, we will measure error and uncertainty in our setup, and we will do this by observing and quantifying bias and precision errors from our equipment, the LiDAR, the stepper motor, our DAC, and measurements to determine how uncertain our volume and calculations are. Basically, by calibrating our setup, we'll get an uncertainty in the LiDAR sensor, which will measure our distance, R, which will be used to calculate the area of our object, and then the uncertainty for the stepper motor will give us uncertainty for our height h, and those will propagate through our governing equation for volume, which will be base times height, which will give us an uncertainty for both of those. Probability and normal distribution, we expect the distribution of our measurements to be Gaussian. So probability and normal distribution, we expect that the distribution of our height and distance measurements to be Gaussian. So all the data that we collect from our scanner and from our height, we expect it to have a Gaussian distribution. And that will allow us to determine confidence interval for our measurements and a confidence band for the accuracy of our 3D scanner for comparing the volume of the measured object to the volume of the actual object. We also use sample statistics, and we'll do this by taking a minimum of 30 data points for each of our measurements in the distance and the height, and determining the mean value, the distance, and the uncertainty using sample statistics. We're not expecting any outliers in our data, but if we have outliers, we can analyze them using Chevanot's criterion to help us determine if the data point should be included within our data set.
Some more topics we cover are, first, our uncertainty propagation. We'll carry bias and precision uncertainties through our volume equation V equals A cubed to see how measurement error affects results. We're not going to be using student's t since our 3D scanner provides over 30 samples, letting us assume normality. For chi-squared, we'll test if our data is Gaussian rather than us running a full hypothesis test. And finally, for system response, we'll assume any error from equipment timing is negligible.
So these are some of the variables that we'll be doing in this experiment. With it being a 3D scanner, we will have different measurements depending on the specimen that we are looking at, but for this example, we are looking at the cube that we scanned. It's a 3 centimeter cube. So the variables that we're paying attention to are the height, the distance from the LiDAR sensor to our specimen, and the angle theta. We can obtain our height z and our angle theta from information of our stepper motors and their positions and the rate at which they're turning. We can obtain our distance to whatever object we're scanning from the NI DAC in the basic lab view. And we're expected to fall within a 5% error of the true volume. While scanning the cube, we will measure a maximum distance of 28.5 centimeters to a minimum distance of 27.88 centimeters away from the LiDAR sensor.
In this slide, we're going to discuss the source of errors and gaps to be assessed. For precision error sources, we know that there can be discrepancies in the distance of the LiDAR and also the height readings. This may result from sensor noise, vibrations, or other minor alignment changes. For the bias error, we know that there can be calibration issues with the LiDAR sensors, as well as sensor misalignment, or even just small inaccuracies in the stepper motor. First, to minimize the precision error, we plan on taking 30 measurements to be able to determine the uncertainty of the measurements, as well as being able to create a bell curve on that. And for the bias error, we plan on calibrating both the LiDAR sensor and the stepper motor. Some of the gaps that might occur are issues with centering the object, as well as the vibration of the motor, the placement of the LiDAR / centering it on the specimen to get the best data.